systems of linear equations by graphing, but first of all, I wanted you to complete this table. In other words, if we were going to graph these two equations, we could complete a table to help us get some ordered pairs to put on our graph. Okay, so when we substitute these x values into y sub 1, our first equation equals x plus 1, what are the y values that correspond? Run down the table for me. What are they, Noel? What'd you get? So this is 0? Okay. Yeah, you guys got some head shakers here. They don't want to agree. What?
1.
It should be 1 because what did we have to do? We had to add 0 to 1. We put 0 in here, add it to 1. This is really what we were doing. Substituting in for x and we get our y value, right? So what is it for the next one? Let me guess, most of you did mental math, right? What's the next one?
2.
2. And they just keep doing what?
Adding 1.
Going up by 1. So as the x's go up by 1, so do the y's in this one. So we have y values 1, 2, 3, 4, and 5. How about for our other equation, y sub 2, 5 minus x? What's the y value when x equals 0 for that one? 5. What is it when x equals 1? 4. Okay, pairs, there's a pattern going on here too. As the x's go up by 1, what's happening to the y's? Going down by 1. Okay, so let's just fill out the rest of our table here. Okay, so we have 5 ordered pairs really for both of these. We have ordered pairs 0, 1 for the, and 1, 2, and 2, 3, and 3, 4, and 4, 5 for y equals x plus 1. We have 5 ordered pairs for our y equals 5 minus x. We have 0, 5, 1, 4, 2, 3, 2, 2, and 4, 1. Or 3, 2, excuse me, and 4, 1. What's the question I asked on the side? How many ordered pairs do you think are solutions to both equations? In other words, it would satisfy both equations, make both of them true. Are there any ordered pairs in that table that make both equations equal the same thing?
Y sub 1 equals 2 plus 1 that would equal 3. Then y sub 2 equals 5 minus 2 equals 3.
So you're looking at when x is equal to 2, when we sub 2 in. When we sub 2 into the first one, we get a y value of 3. When we sub 2 into the other one, we get a y value of 3. So in other words, they both end up with the same y value given the x value of 2. Do you think there's any other times that would happen? Do you think you can think of any other values for x that if you put them into both of the equations, you'd get the same y value? What do you think? Yeah? Negative 2. Should we try it? Negative 2 is not in our table, so let's try it. Negative 2 plus 1. What is that? What's negative 2 plus 1? That's negative 1. So we're trying negative 2 right now. So we said that's negative 1. Okay, how about in 5, take away negative 2? That's the same as adding a positive 2. So it'd be 5 plus 2. That is 7.
Never mind.
Okay. Think there's any others? We'll ever be able to find another x value that when we substitute it into both equations, we'll get the same y value.
1/2.
Go ahead, just do some mental math with some ones and see if you think you find one. Let us know. Kind of seem, I remember there was this pattern going on. In the first one, as the x's got larger, the y's went up by, as the x's got larger by 1, the y's went up by 1. Well, if we go the opposite direction, as x goes down by 1, what do the y's do?
Go up by 1. Go down by 1.
Go down by 1. And over in this one, we had, as the x's were going up by 1, the y's were going down by 1. Well, what if we went the other direction? The x's went down by 1. What would they do? They're going to go up. Do you think they can ever meet again at the same place?
No.
No. So how many ordered pairs are solutions to both equations? Only 1. And what ordered pair is that?
2.
2,
0. 2.
3.
2, 3.
When x is 2, y was 3 for both of them. That's the only ordered pair solution that is the same in both of them. So I said, let's verify that with a graphing calculator. I gotta see if I still have my graphing calculator open here.
Only ever found that 2, 3.
So what do you think? Do you think that's what they're going to do? They're going to cross at 2, 3?
Yeah.
Okay, so we have 2 lines on a graph, and you think they're going to cross at 2, 3? Let's look at the table here first of all. Does this table correspond with ours?
Yes.
Do our values match up?
Yeah.
Yeah? Okay. Now let's go check on that -2. See how we did with that one. See if we got the right x value or y values for -2. Oops, there I went too far. Did we get the right x values for -2?
Yeah.
Does it appear we're ever going to find another ordered pair?
No.
No? Okay, so let's go take a look at the graph then.
Yes.
So what happened on the graph?
It crossed only at 2 and 3 and were like perpendicular.
Well, are we certain that they're perpendicular?
Is that implied?
It really looks like it.
Oh, how would we know if they were perpendicular?
They have to have a range at 90 degrees. We'd have to know the
Yeah, where they cross, they'd have to have a 90-degree angles. How could we tell though without getting out a protractor and measuring?
Seeing if the slopes are the exact opposites of each other.
Well, they aren't exact opposites. They are, when you multiply them together, you have to get what?
Opposites.
-1. You gotta multiply them together and get -1. Oh, well, let's go back then and let's see. Are the slopes of our lines opposite? Are they gonna, when you multiply them together, would you get -1? What's the slope of y sub 1? 1. X plus 1, that's the slope of 1. What's the slope of the y sub 2?
-1.
Oh, what's 1 times -1?
-1.
Oh, but so not only do these lines intersect at that ordered pair, but they also are perpendicular. But, you know, that's just a consequential thing, something that also just happened to happen, that they are perpendicular. They don't have to be, though, by the way. So what does the table show in our graphing? When I opened up the table in the graphing calculator, it showed the same thing as our table does. And what does our table show? Let's write this down. I want us to put when x equals 2, both equations, that's a great eye there, have y equals 3. The graphing calculator supported it too, it's just as smart as we are. So when x equals 2, both equations have y equal to 3. What does the graph show? So we graphed it with the graphing calculator, we didn't hear. How does the graph support it? What happened on the graph? I know the lines are perpendicular, but do you think that's important right now? Here's what's important. Where did those lines cross?
2, 3.
That ordered pair 2, 3. So the lines intersected at ordered pair 2, 3. So for both of them, when you go to x equals 2 and follow it up to the line, you land on a y value of 3. So the graph shows it, just like the table does, that when x equals 2, y equals 3, with both of them working together. So here's what's important for us to, first of all, get a grasp on that we're going to be working with in this chapter. Systems of equations, what are they? So what's a system of equations? I didn't make you read ahead. So when 2 or more, you can have more than 2 equations. We're only going to work with 2 at a time most of the time here. When 2 or more linear equations containing 2 or more variables, we're only going to work with 2, it is called a system of linear equations. And systems, when we can set up a system of linear equations to problem solve when there are 2 or more unknowns, they are very useful tools to help us problem solve when we have 2 unknowns to solve for rather than just 1. So if we can set up a system of equations and then go about solving it, we can problem solve when there are more than two variables or more than 2. Ricky?
So does that mean you could have like 50 lines on a graph?
You could.
Whoa.
Thank goodness we don't have to solve any 50 equation systems.
Alright.
We're only going to solve, at least especially to start with, only 2 lines, 2 equations in our system of equations. But that system of equations means this, class. You have to keep this in mind. System of equations means they have to work together. They have to say, when we work together, what can we say is true? Okay? So a solution of a system of linear equations with 2 variables is always an ordered pair. Always an ordered pair when we're working with 2 variable systems of equations. Where is that ordered pair that's going to make all the equations in the system true? It has to make both of them true. Or all 3 of them true. Or all 50 of them true. When you have a system of equations, you're looking for that ordered pair that makes all of the equations true. And when we're doing it on a graph, we need to find the point that they all have in common, therefore their point of intersection. Just like our graph just supported, where were they intersecting each other? That gives us our solution for our system without having to make a table. So any of this you want to go back and talk about? Okay, then let's go to the back side and let's practice solving by graphing. Okay, here's our system of equations. They put this nice little fancy bracket off to the side. That shows, you know what, these two got to work together. One doesn't get to say, I'm more important than the other. You work by yourself, I want to be by myself. They have to work together. So we have y equals 3x plus 1, and we have y equals negative x plus 5. Are they in graphing friendly form right now?
Mm-hmm.
What form is that called? Slope intercept form. Oh my goodness, we've just done a ton of stuff in chapter 4 on slope intercept form. So we're going to identify the slope and the y-intercept for each of them. What's the slope and the y-intercept plane for the first one? Slope is 3, y-intercept is 1. Okay, Christian, what is the slope and the y-intercept for the second one?
-1, 5.
-1 for the slope, 5 for the y-intercept. Now, when you graph these, hear me on this, because it can get really confusing if you don't. Graph one equation at a time, draw its line, and then move on to the other one. Okay? So let's graph the first one, y equals 3x plus 1. Let's go put a point on our graph where?
3.
No,
1.
1 on the y-axis. And from there we're going to
Up 3 over 1.
up 3, 1 to the right. Or we can go
Down 3 over 1 to the left.
down 3, 1 to the left. And because it had a positive slope, our line should have what kind of behavior?
Positive behavior.
What's positive behavior?
Upwards.
Rising from left to right. So take your ruler now and don't graph any more points starting the other equation. Get this one's line drawn first. And all the way through the graph. Now, stop and say, just like we just did. So many times on the test when I was having to take a point away for people who graphed a negative slope, but yet ended up with a line rising from left to right, I was like, how many times did I say to them, check the behavior of the line against what the slope said it should be? So do we have good behavior for this line?
Yes.
Yes. Okay, then we can move on to the next one. So in our next one, we're going to start at 5 on the y-axis, and we're going to graph with a slope of -1. And sometimes you actually end up graphing on top of a point from the other one, and it makes it very clear to you, or it should make it very clear to you then, what your point of intersection is. Ricky, did you have a question?
Oh, well, I was just gonna say, I always make the second line with circles and the first one with dots.
Oh, so you leave them, you color in on one and the other one you don't?
Yeah.
So you can tell them apart. Okay, that works. That works for you, you can do it. Okay, have we found our solution? Where's the solution at again? At the, what do we look for?
Point of
Point
intersection.
of intersection. Are these intersecting anywhere?
Not on any point.
Oh, I think they are.
They are.
At ordered pair 1,
1, 4.
4.
Okay.
If yours didn't, then something might have gone wrong with your graphing. So that is where they appear like they should intersect
1, 2,
that.
3, 4, 5. Oh, 1.
Okay, now hear me again. When we're solving by graphing, we're only estimating. In other words, you know what? The solution to this could be 1 and 1, 4, 4 and 1, 10. We don't know. We're just estimating, really. So we have to do check problems. And Yes, you have to do check problems, those few that you have to do tomorrow. I'll let you out of them today, we're doing them, okay? So check. So we think the solution is ordered pair 1/4. It has to check in which equation? Both of them. It has to check in both of them. So we write down both equations and we substitute into both and make sure it legitimately checks out. And just a substitution step is not enough. You need to actually calculate your way down and not with a calculator. So what's going in for y? 4. What's going in for x? 1. So from our ordered pair,
4 equals 4.
4 equals, well, first of all, what's 3 times 1?
1.
3.
3.
What is 3 plus 1?
4.
4. Yeah, I know you can do mental math, but here's what students tend to do. Do a substitution step only, and then they put, well, yeah, this side's supposed to equal 4, so I'll just write 4 equals 4, check. And then I look at their work and I say, that doesn't become 4, that becomes like -7. How can they put 4 equals 4 when that's not really what their work supports? So we need to actually put it in and make sure it works, okay? And then y equals, this one we'll put in 4 for y. That negative sign is not part of the x. The x gets a 1 substituted for it. So the negative sign is not part of the x is 1. 4 equals, what's -1 plus 5? 4, because we want it to be or because it legitimately is? Both, right?
Legitimately is.
-1 plus 5 is really 4. You'd be amazed what I see on student papers. You know? So now we can say, you know what, feeling pretty confident that the solution is ordered pair 1/4. Okay, questions about that one? That was a friendly one because both of the equations were in slope intercept form, graphing friendly form. How about the next one? Are those in graphing friendly form?
No.
Not really. So we're going to put them in slope intercept form. So let's start with the 3x plus y equals 4. What should we do?
Subtract 3x.
Okay, subtract 3x from both sides.
Yes.
So what's our equation read now? Y equals what? 4 minus 3x. Also known as?
Y equals -3x plus 4.
Yeah, it's also known as -3x plus 4, if you like it in the true mx plus b form. Okay, so what's its y-intercept? M is, or y-intercept. What's its slope and y-intercept? What's its slope?
-3.
-3, and its y-intercept is 1. Let's just go ahead and do that one before we even work with the other one, okay? Let's get that one graphed.
Wouldn't it be 4? The y-intercept?
Yeah, that'd be a better y-intercept. Go with 4. Okay. Thanks for catching it before I started graphing. Then I go south. There was a negative slope. My line is falling from left to right. As I move on, do I feel good about the behavior of the line versus what the slope was? Yeah, okay. As long as we put it in slope intercept form correctly, I'm thinking that, you know, so far so good. Okay. So now we're ready to get our next one rearranged. What should we do first in that one? X minus 2y equals 6. Do what? Add an x to both sides? It's tempting to want to do that because there's a subtraction sign behind it, but we can't read subtraction backwards. We can't say that equation is the same as 2y minus x. So maybe the thing to do right away is change this to add and the opposite, so it would be a -2y. Now we can read it backwards. Negative 2y plus x, what should we do? Subtract x. Trust me, guys, I'm starting to feel better about your graphing, but I'm not so sure we're really good about putting equations in slope-intercept form really correctly yet, so let's be really careful there. If you don't do this correctly, you set yourself up for probably getting a wrong solution also. So now we have the equation negative 2y equals 6 subtract x. Again, I'm going to suggest that we change this subtraction to add the opposite. So minus x plus a negative x. Trust me, it's going to go a whole lot better for most of you. And then we will say, okay, now what do I have to do to every piece of this equation? Divide by negative 2.
Y equals negative 3 plus 1/2 x.
So y equals negative 3 plus, because a negative divided by a negative is a positive, and that's a 1 in front of that x, so you're right, it would be 1/2 x. AKA, for those of you who like it really in good old, this is slope-intercept form, oopsie, yeah. Okay, what's our slope? 1/2. What's our y-intercept? Can I trust you guys this time? Okay, let's go put that on our graph. This would be why we warmed up with graphing in the homework for today. We can't graph, we can't solve systems of equations by graphing. Does there appear to be a solution? Why do we say there's a solution? Because what?
Crosses at a certain point.
Because they're intersecting at, and what's the order pair that's intersecting at, Michaela? 2, negative 2. So we believe this graph is leading us to believe that the solution is 2, order pair 2, negative 2. But until we really do a check problem, we're not really certain. So, but stop, because you're already, some of you are already starting to check, aren't you? Anybody already starting to check? Okay, here's where you gotta check it at. Here's where you stop. If you check it in the slope-intercept form name, and it checks out, you're like, cool, I got this, and then you come to class tomorrow, and you're like, well, Mrs. LeGrand, I got a different answer, and mine checked out. Well, here's the reason yours is going to check out. If you put it into slope-intercept form incorrectly, you're checking your answer in your incorrect equation, and it's going to support your incorrect answer. So you need to check it where?
In point slope form.
Not point slope form.
Whichever form
What form
is
was
in.
it? What was this given in? This was given in standard form, so we're going to check it in its standard form name. So we have to check it in 3x plus y equals 4, and we have to check it in x minus 2y equals 6. That's where we're going to check it, because that will truly show us, you know what? If it checks out here, I'm feeling good about everything I did. If it doesn't check out here, you know what? Chances are
everything again.
Chances are you didn't put it in slope-intercept form properly. And that's going to stink, right? But that's what you should be checking out. So we need to put 2 in for the x, and we need to put negative 2 in for the y.
2 minus 2 times negative 2.
So go ahead and do your checking. I'm going to suggest over here, where was that? Remember when we changed it to add the opposite? I'm going to suggest you do the same thing for the checking.
Oops.
In that second equation.
No, it's still a
Do I have to come and make sure you're showing enough steps in your check problem, or can I trust you? 6 plus negative 2 equals 4. Class, help me out, what's 6 plus negative 2? 4.
Oh.
Checks out in the first one, cool. 2 plus negative 2 times negative 2, that's 4. 2 plus 4 checks out in both of them.
Bless you.
Am I going to consider it a check problem tomorrow? Be a substitution step and then that little 6 equals 6 or negative 1 equals negative 1 or think that's gonna work? No. I'm gonna be like, sorry you don't get to start your other homework yet because you have more to do. So legitimately check it, in other words, make sure you really are not just putting some pencil marks down to make it look good and moving on. Okay, anybody have any questions?
I'm not done.
Okay, why don't you get out a sheet of loose leaf paper, and that's where you're gonna show everything except the graphing. Okay, so getting it ready to graph M and B, and then identifying the solution, and then last but not least, you'll come over here and, or in between, I guess, you'll get the solution from here when you graph it, and then you'll go back to your loose leaf and do a check problem.